Hello folks, my name is David with Expat Audio, and this is the second video we're doing to do with haptics, to do with our Earl Grey boards that we have in development. In this video we're going to look at how we measure vibration in haptics. We're going to look at the mechanical construction differences between LRAs and ERMs and how that impacts the drive signals we put into them. We're going to look at how we create the various vibration patterns and the envelopes that go with them. And then also look at the sort of streaming the patterns into the device versus storing the patterns on chip. And from there we'll discuss haptics as a user interface language. So if you like what you see, share, like and subscribe using the buttons below, but also come along and find us on Facebook and Twitter. Let's get started. One of the first things we want to think about is isolating vibration so that we can measure it properly. So we've got our eval kit here sat on some foam, and the foam isolates the item that's vibrating from the rest of the bench and everything else. You're not trying to get the bench to vibrate, you're trying to get just the board itself. Now the board itself in this case, between this and a metal mass that is below it, weighs 100 grams, which is the equivalent of a cell phone. And what we have on here, right over here, is an ADXL335. Now that is an analog output accelerometer. It measures acceleration and vibration for us. So we're going to look on the scope in just a moment here. We'll look over in a moment and see the vibration that is caused by our device driving the LRA. On this particular eval kit there are three different kinds of outputs. There's the out P and out N, which I use to drive the vibration motor itself. We've got a filtered out P and out N because the PWM rate of these is up in the hundreds of kilohertz, and so we want to filter that down so we're only looking at the signals being driven into it. And then we've got the accelerometer output. Now you can see here that I have two scope probes connected. One is actually to the out P signal, and the other one is connected to the accelerometer itself. So what I'm going to look at, I'm going to trigger my oscilloscope from when out P starts switching, which is when we start driving power into the LRA, and then we're going to see how that is reflected in the accelerometer output. There's two traces on the scope you can see here. Down here is the output from the device. It's actually a bridged output, but in this case it's only I'm only measuring one side, so the other side is actually filling in the gap here. And then in yellow here what you see is the output from the accelerometer. The board itself is vibrating up and down at the same rate. Now what I'm about to do here is I'm about to start the vibration, and what you're going to see is the vibration slowly ramp up from 0 to maximum. So what you can see here is that it's a mechanical system. Despite the drive signal being more or less constant, there's a little DC drift here due to the way I'm measuring it. But what you see here is the vibration doesn't hit maximum immediately. It takes a couple of cycles for it to go from no vibration at all to maximum vibration. Now this is with an LRA, it's done it within about 3 cycles, but with an ERM that's going to take much, much longer. I've now hooked up an ERM. It's a coin one that's on the board, and I'm going to trigger it again, and you're going to see in this case it's a lot more erratic, but not only that, it takes a lot longer to come up to speed. So you can see here the drive signal started here, and you can see it's taking a lot longer to get up to speed here. So if the divisions are 20 milliseconds each, you're looking at 1, 2, 3, 4, 5, 6, 7 until it gets somewhat constant, so 140 milliseconds or longer. If I change the horizontal position, you can see that it settles into higher amplitudes much later. So that's the trouble with an ERM. It takes a long time for things to settle and for things to be consistent. In this next section we're going to look at how LRAs are made and how they're different from other products. I'm going to jump to a couple of different websites here from the LRA manufacturers because they tend to show it best. This first one's from precisionmicrodrives.com, and you can see here we have a spring, a moving mass, which is typically the part of it is made up of a magnet itself, and then a voice coil. And essentially this behaves like a loudspeaker, which means to move this mass back and forward we need an AC signal, right? One to move it forward, the other one to move it back. And it means that it actually has a pretty sharp resonant frequency. There is a special frequency with these LRAs that if you drive it at that frequency it moves a lot, but if you're off resonant frequency it means you move very little. And we'll see that in just a moment in the data sheet for the product. Now to see one actually moving, I'm going to jump over here to M+'s website, and you can see in their animation that they show that mass moving up and down along with that spring and so on. In this next section here you can see the resonant frequency of the LRA. Okay, so what you see here on the x-axis, you see frequency, and on the y-axis here you see vibration amplitude. So this is showing the number of G's, as in like G force is 1, is equal to 1 G on Earth. And so you can see here, if you drive at this magical frequency, you'll get 1.4 G's of force. But if you're off by 10 hertz or 5 to 10 hertz, you drop comfortably down to almost half of that. And so tracking resonant frequency is very, very important. Now, what makes this really special is that this resonant frequency is not static. It doesn't stay where it is. So depending on the grip on the product, depending on the amplitude that you're trying to drive, will shift this up and down, along with temperature, along with age, manufacturing, and so on. So we really want to do our best with these products to track this resonant frequency as quickly as possible. So when we create the various patterns that we want, driving specific frequencies really doesn't help us, because for all you know, on that day with that particular motor, you could be off by 5 to 10 hertz, and we've seen here that being off by 5 to 10 hertz can actually hurt our output force significantly. So what we tend to do is drive envelope levels out of the product. Now, when we look at the resonant frequency of a device, for instance, on the standard eval kit, we use one from Java. The target resonant frequency may be 169 hertz. That's from the datasheet for the product, along with absolute maximum nominal drive voltages and current and so on. But one of the things, I've got this here in direct register override, where we're simply sending the amplitude that we want between 0 and 1. Think of it as between 0 and 100%. And what I want you to do here is to watch the resonant frequency here update in real time as we turn it up. So you'll see at very low amplitudes, it's at 150 hertz, and it climbs progressively. And it's compensating here, right? So as I go up to about almost 100% here, it'll flip polarity in a moment, so I'm quite careful. We're at 164 hertz. Now, if I, for instance, now grab the eval kit, or I put pressure on the motor, watch this. I'm pressing down on the motor now and changing the mechanical coupling. And with that, I'm able to shift the resonant frequency. Now, because that resonant frequency can change with amplitude, it's very important that we don't simply treat this as an open loop driver where we just send, the resonant frequency from the datasheet and blindly just drive it. You can see here I'm off by 12 hertz, which could be a significant amount of power. So it's important when we design the haptics patterns and the events that we want to drive, that we drive different envelopes of vibration and then let the driver IC do its job of tracking that resonant frequency. In this particular GUI, and it's different with every type of device, whether it's from Dialog or from other suppliers, we can actually see the waveform memory editor. Now, some devices have this, some don't. What you can see here is these are being imported from the device, read back from memory. These are a bunch of the envelopes and patterns and so on. Okay, so what you'll see here, for instance, is there's a short 20 millisecond vibration here, and then it drops back to 0. In this case, we actually have what feels much more like a heartbeat effect, where you have like one small triangular envelope followed by another much larger one, and these can be tuned so they can be on resonance or off resonance. We can change the amount of time it takes. So if I want this to be a very slow ramp, then I can change this to take much longer or much shorter. Now, bear in mind, an LRA is a mechanical system, as we've talked about before. So if you make an event too short, it doesn't have enough time to get the LRA up and moving, up and spinning, if you will, up and vibrating. Now, in this particular case, these waveforms and the envelopes, if you will, are actually being stored in the memory of the device. However, very complex patterns you may want to actually store in your host microcontroller, right, in your Arduino, in your Raspberry Pi, and so on, and stream it in real time, over I2C, streaming that amplitude value and replacing the value over and over again. And so, if you're doing very complex things like gaming, where you want real textures as you're running across a path or something like that, then you may actually want to do that using streamed haptics. So you can do way more complex things by streaming into the device. However, you pay the penalty then of keeping your I2C bus too busy. So if you have a very busy I2C bus looking after many other sensors and so on in the system, you may want to decide to put these effects in your device and store them as memory. Now, the DA7280 has about 100 bytes of RAM, and it treats these patterns in a very smart way. So here we've got about 58 bytes of RAM used for 1, 2, 3, 4, 5, 6, 7 different patterns in the device, and these can be replaced in real time as well. So if you're jumping between different use cases, you can download new patterns into the RAM, and off you go from there. Now, as you can see, haptics is way more than just a rumble for a notification or a click for a notification. What we're talking about here is a very sort of analog, high definition experience that becomes possible. These 3 patterns here may look like a simple square wave. They actually represent, this is a very light, sharp click, whereas this might be a bigger thud, a bit more of a click with it. And then heartbeat effects. These are notifications like a click buzz, which could be used to represent turning up the maximum volume or turning up your air conditioning. And when you do finally hit that maximum, you get a tick to really communicate that you've hit maximum volume and so on. And so it's with this technology, it allows us to really begin thinking about haptics as a language. Today you can buy an Apple Watch, and if you use the Maps application on the watch and with the phone, it taps once for turn left and taps twice for turn right. That's a very simple example, but with that technology, and if you extrapolate out further, for those of you that have sat in a Tesla, Teslas are wonderful, but the touchscreen today has no haptic feedback, so you always have to look down. Whereas with haptics, you could, for instance, do finding the edge of a switch, right? Running your finger down, feeling the edge of the switch, and then pressing and holding to activate it, and then feeling that click back or another different pattern to tell you, okay, the air conditioning is on, the rear window heater has been switched on, and so on, and having a different haptic feeling that communicates to you with every motion that you make. So in our next video, we're going to look at how do we integrate this with a CapTouch board. There's a number of small hobbyist boards for CapTouch. We'll see how we hook that up to the board. We're going to see how we use this kind of device with an Arduino. What kind of libraries do we need? What functionality is available? And then we'll also evaluate a lot more of the vibration using one of the ADXL 335s.